Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Kumar Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button and share it with your friends who are preparing for their boards and competition as well. Alright, subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. And also visit our website www.v-learning.in. All these live classes what we are providing here you will be getting there. Along with that you will be getting lecture notes also. Okay, you can download it, read it from there. It will be very useful for you. So do check out our web application. All right. Now without any delay, let's get started with today's session. We were doing moving charges and magnetism, and this is lecture number 2. In this particular lecture, we are going to talk about magnetic force on a current carrying conductor. Alright, now let's start. Magnetic force on a current carrying conductor means if a current carrying conductor is present in a uniform magnetic field, how much force it will experience, right? First of all, do you think that if, let's say, there is a magnetic field, what does this cross means? The magnetic field is inside the board. Clear? Let's say there is a magnetic field, or let me make it easy for you. Let's say there is a magnetic field like this. All right. There is a current carrying conductor in it. Or I'll make this only. Fine. Do you feel now current is flowing in this direction? Let's say this is current. It is flowing. Do you feel this conductor will experience any force? Let's understand it. See, if the current is flowing in this conductor, that means there are charges inside this conductor. And we have seen in the last lecture, when I was explaining about Lorentz force, I told that if any charge is present in a magnetic field, it will experience force, right? If that charge is moving. If it is static, if it is at rest, it won't experience any force. But if the charge is moving and it is inside a magnetic field, it will experience force. Here, if you see inside this current carrying conductor, current is flowing, that means the charge is moving. Yes or no? Now, if the charge is moving, which charge is moving? E. Electrons are moving basically, right? Okay. So now let's say there are too many electrons. Now, electrons and current direction is opposite. Right? If current is in this direction, electrons will be moving in this direction. But we can assume that the positive charge is moving in the direction of current. That means E plus is moving in the direction of current. I can assume that, right? So basically this is something where electrons, charges having velocity are moving in this particular direction and they are in the magnetic field. So if I talk about one single electron if I talk about, let's say this is one electron, it is having charge E plus, okay? It is going in this direction with some velocity. Acha, what will be the velocity by which this electron will be moving? Current, right? If you remember, when we derived the formula for current from classical theory of current, from classical story of current, I is equal to NEAVD, where VD was the drift velocity. If there will be current in this conductor, these electrons are moving with drift velocity, that is VD. So here this velocity will be VD, right? There is a magnetic field in this direction. Now magnetic field is there, a charge is moving with VD, this charge will experience force, right? What will be the force with which this charge will experience? F is equal to QVB, right? F vector is equal to Q V cross B. Remember in the last session I told again. Now here the charge is E, velocity is VD and magnetic field is B, right? That is equal to E VD B sine theta. This is the force that will be experienced by this one electron. By one electron. We have to find out force experienced by this entire conductor or this entire wire. Okay, how do we do that? Acha, can you tell me the direction of force on this particular electron? Right hand palm rule. right hand palm rule. The fingers in the direction of magnetic field. The thumb in the direction of motion of positive charge. The thumb in the direction of motion of positive charge. Okay. So now if I place the thumb like this, the direction of palm will give me the direction of force, that is inside the board. The force will be towards inside the board. Clear? So each electron will be experiencing force inside the board. Something which is pushing it from here, or you can understand if I'm standing behind the board and I'm pulling the electrons like this, right? So this entire conductor will experience force inside the board. Yes or no? Fine. There are more ways also to find the direction of force on this conductor. I'll tell you later on. Okay. One way is right hand palm rule. Now, so this was the force on one electron. I need to take out force on this entire rod. So what we'll do is, let us take a very small element. Here I'll take a small element. Let's say dl. All right. For one electron, I know in dl, how much will be the force? If we get to know the number of electrons in dl, we can get to know the force. Let's say in very small element dl, the force will be df. Okay. That df will be equal to, force on one electron is this. If n electrons are there in dl, so force on n electrons will be n into this force. Ne Vd B sin theta. Correct? Force on one electron is this. One positive charge, let's say, positron, right? Force on one positron will be this. So if n charges are there, n e plus are there, then n into this, right? N charges are there here. Now, this n, how do we get the value of this particular n? If you remember, for any conductor, we know number of charges per unit volume. Correct? We don't know this, but we know in a unit volume how many free electrons will be there. Correct? If you remember, n is equal to number of electrons per unit volume. Remember? Now for this, this is electron density. For this, if I am taking this particular element, if I want to write the volume of this, what will be the volume? It is like a small cylinder only of length dl, and the area of this will be A. So this volume will be this area into this length. Correct? A into dl. This will be n upon A dl. So n is equal to, capital N is equal to n A dl. Clear? So from here I can write df is equal to n A dl into E Vd B sin theta. Correct? Now this is a very small force, df. This is a very small force, df, on this small element dl. Now to get the force on this entire conductor, what I'll do, I'll integrate this df from here to here. Correct? Now, df is equal to n A dl E Vd B sin theta. Correct? Now see. So force on conductor, that is equal to integration df, that is integral n A dl E V d B sin theta. From here what I'll get, this will become f. Integral df is f. From here n will be constant. This is free electron density. A is constant. E is constant, charge on one electron. Vd is constant, drift velocity. B is constant, it's a uniform magnetic field. Theta is also constant. See here. What is theta basically? What is theta basically? Theta is the angle between the conductor and the magnetic field. Here theta was the angle between velocity and B. This is theta. The angle between, if I am talking about one charge, point charge, the theta will be angle between the velocity vector and the magnetic field vector. If I am talking about conductor, again the same thing. Since VD is in this direction, you can think that it is VD, the angle between VD and B. But it is easier to understand this way, that is the angle between the conductor and the magnetic field. Okay? That is theta. So theta is also constant. If you see here, or for this small element, or here, everywhere it will be theta only. This entire thing. Correct? Theta is constant, that means this will be sine theta. What is not constant, what is variable, what we have to integrate is just this dl. And dl we have to integrate from 0 to L. Right? From 0 to L. I am taking this length from here to here. This is L. Right? From 0 to L. If I integrate this from 0 to L, it will be L. So this is basically NAEVD sine theta into L. Or I'll write L sine theta. Clear? Now what is this? Just see, a very beautiful formula will come. What is this? NEAVD. I is equal to NEAVD. Are yes or no? I is equal to NEAVD. This we have already learnt. So from here, can I write this as IBL sine theta? This is the formula for force on a conductor. This is the formula for force on a conductor. रात की 2 बजे भी ये formula याद होना चाहिए. Clear? Very important. Many questions can be formed on this formula. All right. Note it down. Now see, from here, B is a vector, we know. L also we can take as vector only. From here to here, if I assign the direction for L, I can take it as vector. Now this is written IBL sine theta. If with two vectors, this is basically the magnitude of two vectors and sine theta. It is cross product, right? If it is written AB sine theta and I know A are vectors, A is a vector, B is a vector, I can write it as A vector cross B vector. Are yes or no? But now one more thing. I can write it as B vector cross A vector also. See, this will also be BA sine theta, this will also be AB sine theta. That is the same. So what should I write here? What should I write here? Here, there are two possibilities. It can be I B vector cross L vector, or it can be I L vector cross B vector. What should I write? What will be the formula? The formula will be only one, because we know in vector, if I am writing this is different and this is different, correct? Both are different. What will be the correct formula? Basically, this cross product also gives us the direction of the resultant, right? From here, whichever direction will match the actual direction of force, we'll take that one. Now, what is the direction of force here? We already saw it is inwards, inside the board. Magnetic field is this. The fingers in the direction of magnetic field, thumb in the direction of current. Basically, thumb has to be in the direction of perpendicular component of current. Current is this, in this direction, right? See? So there will be two components, one horizontal component, one perpendicular component. So if this is B, perpendicular component of current is upwards, the direction of palm will give me the direction of force, that is inwards. Clear? One more way of getting to know the direction of force on a current carrying conductor. Fleming's left hand rule, you have studied in your 10th standard. Fleming's left hand rule, if you remember, this is father, this is mother, this is child, right? Mother means magnetic field. This first finger, forefinger in the direction of magnetic field, this finger in the direction of current. What I told, always in the direction of perpendicular component of current. Okay, so here perpendicular component of current is upwards. Thumb will give the direction of force, which is inwards. So there are two ways. Either you can use right hand palm rule, or you can use Fleming's left hand rule. All right. Now, inward cross product. Do you remember to find the direction of cross product? If I'll tell here. Okay. If there are two vectors, one vector is A, one vector is B. A cross B, if I want to do, what direction I'll get? Keep your fingers in the direction of this first vector, which is written first, and curl it in the direction of the other vector. A is here, B is there. I have to curl it in the direction of B. The thumb will give me the direction of the resultant. Okay. If I am writing, see, A cross B, if I do, the resultant will be inwards. If I am doing B cross A, this is inwards, this is outwards. See, try. B is in this direction, A is this side is A, right? If I curl it in the direction of A, thumb will be outwards. So if I do this will be inwards. If I do this will be outwards. Both are different, right? Here also, we know here the force is inwards. So we need to get that one where we get inwards, the resultant as inwards. L cross B, if I do, L vector is this, B is this, L is this, B is this, right? What is L cross B? L cross B. I have to curl this in the direction of B. The thumb will give me the resultant, and that thumb is coming inwards. That means this is correct. This is correct. And this one is wrong. Why? Just see, B cross L. B is this. If I curl it in the direction of L, I am getting this thumb outwards. But actually the force is inwards. So this is wrong. Clear? So basically the formula for force what we got finally is F is equal to I L cross B. Where always remember L vector will be in the direction of current. Clear? Very important. Remember in vector form, instead of IBL sine theta, remember in vector form you will always get the direction also. So now there are basically three ways to get the direction. First, right hand palm rule. Second, Fleming's left hand rule. Third, by seeing this L cross B, right? One more, screw rule, if you remember. In cross product only there was one screw rule. Rotate the screw in the direction of other vector. Correct? So here you have to keep the screw here and rotate it in direction of B. Where it will go? It will go inside because you are tightening the screw. But if you rotate it in direction of L, it will start coming out, right? And the force is inwards basically. I hope you know screw rule, right? So there are total 4 ways to get the direction. Properly, if you see, there are 3 ways: right hand palm rule, Fleming's left hand rule, and by seeing the cross product, by seeing the direction of the cross product. All right. Now, if I ask you, okay, for direction, I'll note it down. One is right hand palm rule. Right hand palm rule. Suppose this is your right hand. Right? 1, 2, 3, 4, 5. 5 fingers only we have, unless you are Hrithik Roshan, right? Okay. So now, this Fingers in the direction of magnetic field. Thumb in the direction of current. Palm will give the direction of phase. Or let me write only palm. Some people will think palm doesn't have face only. Acha, when we are talking about only charge, thumb will be in the direction of positive charge, remember. Okay. Or second is Fleming's left hand rule. Or L cross B. Clear? Three ways of getting the direction. Now, all right, 1, 2, 3. Okay. One more thing. What will be the maximum force that a conductor can experience if it is kept in a uniform magnetic field? Think logically. From here, F is equal to, if I only talk about the magnitude, F is equal to ILB sine theta or IBL sine theta. For maximum force, sine theta has to be maximum. Maximum sine theta is when theta is 90 degree. When theta is 90 degree, sine theta is equal to 1. F is equal to IBL. Are yes or no? Nahi aaya. See, very easy. Here only I'll tell you. For F max, theta is equal to 90 degrees. So F is equal to IBL sine 90 degrees. That is equal to IBL. Very important formula again. Why? Because in your course, in boards, 90% of the questions will be on IBL. In boards, 90% questions will be on IBL. Okay. Anyways, if you remember IBL sine theta, there is no need to worry about IBL. You just have to see the angle. Okay. Theta 90 means the angle between L and B. Here, if I keep this as like this, it will experience maximum force. And when will it experience no force? Minimum force. For F minimum, theta is equal to 0 degrees. F is equal to IBL sine 0. That is equal to 0. All right. That is equal to 0. So from here, if I keep it parallelly to B, the force experienced by this conductor will be 0. I hope you got this full properly. Note it down. Now, let's go further. Find the direction of force. We'll do some 1-2 questions to make your concept more clear. So here, this is a conductor having current I which is going upward. This is the magnetic field. Can you tell the direction of magnetic field? It is going inside the board. Inside the board, right? Now, how to tell the direction of force? Right hand palm rule. Fingers in the direction of magnetic field that is inside. thumb in the direction of current, that is upwards. What is the direction of force? The palm will give the direction of force. The palm is facing this side. See, this is the palm. It is facing this side. So the force will be, the direction of force will be this. Clear? Easy? Another way, Fleming's left hand. Father, mother, child. M. Magnetic field, this finger in the direction of magnetic field, this in the direction of current, then thumb will give the direction of force. See, we got the same, right? All right. Another L cross B. L is in the direction of current only, right? This is L. This is L. So L is this side, B is inwards. If I rotate this, curl it inwards, thumb will give me the direction of force. Every time the force will come here only. So any which way you can use to get the direction of force. Next, here can you tell the direction of force? Now this time the magnetic field is outwards. So fingers in the direction of magnetic field, thumb in the direction of current, palm's face will give the direction of force. This time my palm is facing upwards. So the direction of force will be this. Clear? From left hand also, magnetic field, current, thumb will give the direction of force. Got it? Now let's calculate some forces. Find the force on the wire. So this time, the length is given as L, current flowing is I, angle between magnetic field and this is given as 60 degrees. No. Okay, this angle is given as 60 degree. Now you have to tell force. How to do it? How to do it? See, F is equal to I B L sine theta, correct? I B L sine theta. Now here, current is this, that is I, B is given as B, L is this, sine 60 degrees. But that theta is angle between some, it can be I into B into L, sine 60 is root 3 by 2, correct? IBL into root 3 by 2. Now theta is the angle between the current and B, right? Or L and B. Now L and B, if you see, they are 90 degrees. They are not 60 degrees. See here. L and B, if you see, they are 90 degrees. This is B. See L. L is this. L is this. This is B, which is going inside. The angle of this L is 60 degrees with this horizontal. But actually my B is going inside. So angle between this and this, if you see, this is 90 only, right? See this angle. It is like this. This is tilted. But with respect to this, this is 90. So here it will not, this answer is wrong. The answer will be how much? I into B into L sine 90. I'll write the wrong one also so that you understand. See here. I B L sine 60 degrees is wrong. This angle is between L and B. Clear? L is in this plane, B is this. So it is 90 only. So answer will be IBL. That is it. Clear? Got the point? All right. Next. This particular question. Now, how do we find the net force on this wire? See this wire here. Acha, here what will be the direction of force? Thumb, fingers in the direction of this current, and force is this. Here, there will be again two forces, one on this wire, one on this wire. We'll take the resultant of both the forces, we'll get the answer. For this, what will be the direction? Magnetic field is this, current is this, palm is this. So this will be F1, let's say. Here, magnetic field is this, current is this. Okay, one second. Magnetic field is this, current, thumb is in the direction of current, palm will give me the direction of force, that is this side. So F1, F2 we have to take out, then F1 is this, F2 is this, we will take the resultant which will come somewhere like this, it depends on the magnitude also. Okay. Let us first take out F1, F2. F1 is equal to I into B into L sine theta. What is sine theta? Again, it's not 30 degrees. It is 90 degrees. Sine theta is the angle between the conductor and B. Conductor is this. B is again going inside. If you see, it is perpendicular only. This is tilted with respect to this horizontal, but this is 90 degrees, right? So here this will be IBL sine 90. IBL sine 90 degrees, that is IBL. F2 is equal to IBL again sine 90. Correct? This is having this rotation with horizontal, but with magnetic field it is perpendicular only because that is going inside. That is again I into B into L. So this is IBL, this is both are same, F1 and F2 are same. So resultant will be, this is F1, this is F2. Let's say both FF because both are same. So our resultant will be this side, that is root 2F. Correct? Will it be root 2F? No, we have to see the direction also. Let us see. We have to see the angle also. This is 30, this is 30. So this both will be 120. This both will be 120. So F net is equal to under root of F square plus F square or F1 square plus F2 square plus 2 F1 F2 cos 120 degrees, correct? That's how what we do. So this will be, let's say F square plus F square plus 2F square. Because it is same, I am writing FF. Cos 120 is cos 180 minus 60, that is second quadrant. Cos 60 is half. 30, 30, 60. No, one second. Am I seeing the angle correct? This is 30, this is 30, this is 90, this is 90. So this will be 90, 30, 120, this is 60, this is 60. Correct only. Right? Or this is 90, this is 30. (30, 90, 120, 60, 60, 120). Correct. So this will be 120, right? If this is 120, cos 120 is cos 180 minus 60. Cos 60 in second quadrant, that is minus half, right? So this will be minus or let's say plus into minus 1 by 2. Correct? So this will be from here 2F square, this 2 and 2 will be cancelled. So this will come as F. F net is equal to F, see here, 2F square minus F square, that is equal to F. See, 2 cancelled, this will be minus F square, F square cancelled, so this will be F. So force will be how much? IBL, that is equal to I into B into L. In this direction, this will be the net force, this side, F net. Clear? Now understand one more thing. Instead of finding forces separately, one here we found out, one here we found out, what we can do is, there is another way. That way is, we can take the displacement of this starting point and this ending point. If this point is, let's say, P point, if this point is, let's say, Q point, the distance, the direct distance, shortest distance between P and Q, if I take, the direction of current is from P to Q only, right? Here also I'll take from P to Q only. So now if I take this particular distance, how much will be this distance? This is N cos 30, this will be N sin 30, right? That is L by 2. This will also be L by 2. So this entire thing will be L. If there is a conductor of length L, current is going upwards, what will be the force? I into B into L. If current is I, length is L, I be L. That's what we got. And what will be the direction of force? Magnetic field is in this direction, current is this, force is this direction. See, we got everything same. So instead of calculating it separately, what we can do is, we can connect the initial and the ending points. This is basically what we are doing, is we are taking displacement of the length. Fine. And then we are taking out force on this instead of taking separately. Why we can do this? Because if you remember, we got dF is equal to I into B into integral dl. It was NEAVD. Okay, let me write. What we got integral NEAVD into B integral dl, right? Where dl was dl vector, because we took L as vector. So integrating this is giving me displacement vector for L, right? Displacement vector for L. I hope it is clear to you. Fine. So that's the reason we can actually take this displacement vector. Got the point? So I am doing it separately. Here I have explained you, but I'll write it separately. For the same, I'm going to do method 2. I'm just writing it properly so that you don't have any problem in making the notes. Anyways, I hope you have written till here, right? Let me show you method 2 here only. So it was, magnetic field was this. Right? The conductor was like this. Current is flowing from here to here. Current is I. This length is given as L, and this length is also given as L. This is the question. What we have to do is, let's take this point as P, this as Q. So if I join these 2 points, current will be flowing in this direction. From here to here, this length is L by 2, this length is L by 2. I hope you got how we got L by 2. This is L, this is 30 from horizontal. So this will be L cos 30, this will be L sin 30. Sin 30 is half. So this will be L sin 30, L by 2. This will also be L by 2. So this total will be L. Now taking this as conductor, PQ as conductor, what will be the force? I into B into L. Length is L, magnetic field is B, current is I, and the direction of force will be in this direction. Let me mark it with this color. Clear? A short trick. Got the point? Next. Find the force on the wire. How do we do this? Very simple. The displacement vector we'll be using here. Okay? This is first point. Current is flowing from here to here. So basically, if I make this as this, if I join these two, the current is flowing from here to here. I can assume that the current is going like this. This entire thing, I am just assuming it that there is a magnetic field. A wire is kept and the current is going like this, and the length of this wire is this, the radius is r, so this will be 2r. So now I can write the force on this. Force on this will be I into B into L. L is 2r. Or let me write here. Sine 90. Why 90? Magnetic field is inside, current is this side, 90 degrees. That is I into B into L, that is I into B into 2r. This is the force. Alright? Next, find force on the closed loop. In this closed loop, I have to find the force. How to do? Now, if you are taking from displacement vector, what is the displacement of this? 0. If I start from this point, I am again coming back to the same point. Displacement is 0. If displacement is 0, force will be 0. L vector is displacement vector basically. Alright. Another way of doing it, you can find force on each arm. Let's say this particular, if you write the force, magnetic field inside, current upward, this is the direction of force, right? Outwards. And how much will be this force? I into B and length is L, IBL. Here on this wire, magnetic field is inside, current is this, upwards. And what will be the force? Current is I, magnetic field is B, length is 2L. IB into 2L. Here again it will be outward. See, magnetic field inside, current downwards. Palm is giving me the direction outwards. How much it will be? IB into length of this conductor is L. For this particular side, if I write, it will be IB into 2L. Magnetic field inside, current this side. See, it is giving downwards. So, for this entire closed loop, the force is outwards on each and every arm if you see. This and this will be cancelled, completely opposite. This and this will be cancelled, completely opposite. F net will be 0. So like this also you can understand F net 0. Second way to understand, displacement vector is equal to 0. So F is equal to 0. As simple as that. F is equal to I into B cross L, L cross B, where L is displacement vector. If that is only 0, force will be 0. Got the point? So now, this is not only for this rectangular loop what you are seeing. This is for all the closed loops. Any kind of closed loop, any shape of closed loop, the net force will be 0. For any closed loop, write a note. For any closed loop in a magnetic field, F is equal to 0. Make a note of it. Okay, it can be any. I can make a triangle also. If I keep it in a magnetic field, any magnetic field, if the current is flowing, let's say like this, F net will be 0. F net will be 0. Okay. For any closed loop, it can be circular loop, triangular loop, rectangular loop, square loop, any uneven loop. If it is closed, then net force on that loop will be 0. Done? Now, tension in the wire. Again, very important. Do you feel there will be a tension in this particular wire? This is a wire, a circular loop basically, closed loop that too. Current is flowing like this. Magnetic field is B and the radius of this loop is R. Do you feel there will be any tension on this particular wire? Some people will say, sir, the net force is 0. If the force is only 0, there will be no tension, right? That's how we understand. Tension will be there. See, understand. If I take this particular part, just taking it, and if I ask you, what is the direction of force on this part? Magnetic field inside, current this side, upwards. If I take a part here, magnetic field inside, current will be downwards because it is moving like this. Outwards, force. Here, current is moving in this direction. Magnetic field inside, current this side, force downwards. Here also, current is moving in this direction, magnetic field inside, current upwards, force this side. Basically, on every part, the force is outwards. This ring is stretched from all the sides. How will the tension not be there? The ring is stretched. The moment you keep this ring which is having current inside is in a magnetic field, it will be stretched from all the sides. The tension will be there in the entire ring. How to find this tension? Let us take a small element. Let us take a small element. This from this center. I am taking a small element here. This is basically very small element. I am showing you big so that you can see. Let's zoom this particular part. Okay, forget. Let's zoom this and see here. This is the part of the circular loop. Can you see? Once again. This is the part of the circular loop. All right. Now, this is the center, let's say. Now here it is a very small element of some very small angle. If I take from this center, if I divide this part into two, I am taking this side as d theta and this side as d theta angle. Okay. So that my calculation becomes easy. You can take this complete angle also d theta, not a problem. I am just trying to make the calculation easy, that's all. Now see, this ring is stretched, okay? The tension is along the, always if there is a rope which is tied like this, if I am stretching, the tension will be along the rope. If the force is this side, here if I am stretching from this side, the tension always is along the rope only, right? So now here, this entire ring is stretched, the tension is along this side, the tension will be in this direction, This side the tension will be in this direction. It is stretched. Okay. Tension is basically the next particle of this particular rope only is stretching the previous particle. That's all. It's putting force on the previous particle. Right? So now, the force on this is F. This is a small element dl. Now this is so small that I can consider it as a straight line dl. Alright. So this is dl, this element is dl. The force is upward F. Very small. Force is F on this element. Okay. This T will be, let me take two components of this T. This will be, okay. Before that, before taking the component, we should know the angle. This is d theta. How much will be this particular angle? How much will be this angle? It's a straight T. How much will be this angle? Don't you feel this will be d theta only? Why? Why this will be d theta? See, this d theta is between this and this. If there is some angle between two lines, the same angle will be between the perpendiculars from the two lines. Getting the point? See, for this line, this T is basically the perpendicular. For this line, the perpendicular will be horizontal only. This if I extend it, it will be perpendicular only, right? This will be perpendicular, this will be perpendicular. So basically, if you see, this angle was d theta, right? The perpendicular from this is this, the perpendicular from this is this. The same angle will be between the perpendiculars from the same lines. Arey, nahi aaya. Aaya nahi aaya. I hope you got the point, right? So this will be d theta and this will also be d theta. Clear? Try to understand, you will get. Now see. Or understand this way, this is d theta, this is 90. This will be 180 minus 90 minus d theta. 90 minus d theta. This is 90. This is 90 minus d theta. Correct? This is 90. The entire sum should be 180. It's a straight line. So 90, this d theta, this has to be d theta. Then only the entire sum will be 180. See, this is 90. 90 minus d theta. This has to be d theta. 90 will become 180. D theta and d theta will be cancelled. Correct? Now, did you get it? All right. So now I can write this component of tension and this component of tension. This component will be T cos d theta. This component will be T sin d theta. This component will be T cos d theta. And this component will be T sin d theta. I don't know if you are able to see this or not, but this is T cos d theta, alright? Now see, the force is this entire thing is in equilibrium. It is not moving upward, downward, this side or this side. Net force is 0. So that means it is in equilibrium, right? If this is in equilibrium, that means this force, which is upward, will be equal to the entire downward force. And we can see this is T cos theta, that is T cos theta. T cos d theta, T cos d theta. So both will be cancelled anyways, right? We have to equate this force. Since ring is in equilibrium, F is equal to 2T sin d theta. this f will be equal to 2t, this t sine d theta plus t sine d theta. As simple as that. What is this f? What is this f? This is a conductor where the current is in this direction. This is I. This current is I. I into B into the length of the conductor. What is the length of the conductor? This arc, very small element it is. Okay. This arc. This radius is R. So arc will be R into the angle between these two lines, right? This angle. What is the length of the arc? Radius into the angle between this. So this angle is 2d theta. So this dl will be R into 2d theta. This will be I into B. I into B into dl, that is equal to 2t sine d theta. Correct? Till here I hope you have followed. Next, I into B into dl is equal to R radius into the angle of that arc, that is 2d theta. That is equal to 2t sine d theta. Now, since d theta or angle is very small, sine d theta can be written as d theta. This we have already studied. If theta tends to 0, sine theta is equal to theta. We know this, right? We know this. Theta, sorry. So here we know d theta is a very small angle that is nearly equal to 0. So sine d theta will be nearly equal to d theta. Here if I put this, I B R 2 d theta, that is equal to 2t d theta. D theta will be cancelled. 2 and 2 will be cancelled. And finally what we got, P is equal to I into B into R or IRB. Let me write this. Clear? This is the tension in the circular loop. Got the point? Easy question. Very easy it is. Try doing it, try deriving it on your own. This is a circular loop which is kept in a magnetic field. The tension will be I, current flowing in the loop, into the radius of the loop, into the magnetic field. That is constant. Tension is constant. Clear? I hope today's session you understood. In the next session, we'll be doing motion of a charge in a uniform magnetic field. Okay? And motion of a charge in combined electric and magnetic field. See, motion of charge in electric field we have already seen in the first chapter. Motion of charge in uniform magnetic field we'll be seeing. After we get to know this also, then we'll be seeing the motion in combined. Next session will also be very, very interesting. All right? I hope you liked today's session, you understood it properly. If you liked it, do press the like button and share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright, do visit our website, that is www.v-learning.in. In that website, you will be getting all these lecture notes, all these sessions, live sessions, what we are providing here. Along with that, you will be getting session notes, lecture notes also. You can download and read it. It will be very useful for you. Alright. So do check it out. We'll meet up in the next session. Till then, keep learning from V Learning. All the best.